So now let's try to solve these telegraphs equations. Okay, so we'll have to deal with both these equations simultaneously. So we have dou v by dou x giving us minus L times dou I by dou t, right? This is one, and then we have dou I by dou x giving us minus C dou v by dou t. So these are the telegraph equations. Now this course is not a course on solving partial differential equations, right? Nevertheless, it is customary to try and solve this, but by no means is the way that we solve these equations is a standard rule of thumb to solve differential equations, right? So keep that in mind. The Maxwell's equations themselves are based on differential equations, so it is important to learn the science of handling partial differential equations and how to solve them, but by no means is this a course on mathematics, right? So while we will go through the exercise of solving this, because it is a very popular equation or a wave equation that actually shows up in many parts of science, right? Not just in electrical engineering. So it is a very important equation for engineers to know. So we will go through the labor of solving these equations, because remember, we ultimately want to know the forms for these voltages and currents, which are now functions of not just time but also position, right? So we want to get some insight into what these look like, and is it actually truly mimicking the delay that we are after. So the way we start solving this is by taking the derivative, the spatial derivative of the first equation. So if I were to differentiate again with respect to x, I essentially get minus L dou by dou x of dou I by dou t. Okay, and in the rules of differentiation, I can always change the order in which I do them because they are linear operators. I can switch the time derivative and the space derivative, which essentially gives me okay. Now I know an expression for dou I by dou x from the second equation, so I can plug that in here and we can see what I get. So I have minus L dou by dou t, and this I replace from equation 2 with which gives me plus LC dou squared V by dou t squared. Okay, so this equation here is what we call the wave equation. Okay, so I can just write as a separate note here the general form of wave equation. Or maybe we can just okay, where this right? The xx and tt denote the derivative, the second derivative, right? So there's two x's means the second spatial derivative of u, any function u, right? In our case, both the voltage and current can be replaced, can replace the function u here, but nevertheless, the wave equation has the form the second spatial derivative of function u is essentially proportional to the second spatial derivative in time of the same function, right? And the constant of proportionality is 1 over v squared, where we'll understand what that v or velocity of the wave is, right? So this is just a little bit of mathematics so that when you see this form in the future, you can recognize that it is a popular equation called the wave equation, for which the solutions are very well known. Okay, so I can do the same exercise for equation 2 as well, and it shouldn't be very hard for you to use the same technique we used for voltage to do for current as well, and see that the current also obeys the same equation. Okay, so you can take the spatial derivative the second time to equation 2, and then you can swap the order of time and space derivative on the right hand side, and then you can replace dou v by dou x from the first equation, first telegraph equation, and then you'll notice that the current also follows the same wave equation, right? So we notice that when taken the telegraph equations together and solved simultaneously, we actually are led to a common equation called the wave equation for both voltage and current. So before we jump into solving these wave equations, I'll show you a rudimentary solution for the wave equation. We are going to do a small change in variable. Okay, so I'm going to call a new variable tau is x times square root of LC. Okay, so x and tau are essentially just one scale factor of, right? The scale factor being square root of LC. Remember, L and C are inductances per unit length and capacitance per unit length, which are constants for a given cable, right? So if I were to fix the copper thicknesses and the distance between the copper wires, I essentially have a certain inductance and capacitance per unit length, right? So this is a constant scale factor. Okay, so if I were to transform the wave equation after this change of variable substitution, I can essentially say that I have dou by dou tau so the left hand side okay, the second spatial derivative of I can be split apart, right, to change it to be with respect to tau, right? You can do it this way, and of course what is inside can also be broken further, right? So I have dou by dou tau, dou I by dou tau by dou x And what is dou tau by dou x? It is just a constant, the square root of LC. Right? So I can take this out. So I essentially get dou squared I by dou tau squared times dou tau by dou x whole squared, which is essentially LC dou squared I by dou tau squared. Okay, you can probably start seeing why I did this transformation of variables, because on the right hand side also I have a constant of proportionality which is LC, and now I have an LC on the left which both can get cancelled. So I have a much simpler equation where I can say dou squared I by dou tau squared is essentially dou squared I by dou t squared. Okay, where I have essentially just removed the constant of proportionality, right? Okay, now we'll see how to solve this equation. So remember, the wave equation as seen in the last slide, dou tau squared can also be written for voltage. So just make sure that you follow me, right? Even though I might be using I or V specifically, we can choose to solve either, right? The form will remain the same. Okay, so just so that to show that it is completely fair to interchange, let's look at solving this on this slide. Okay, so I have dou squared V by dou tau squared minus dou squared V by dou t squared is equal to 0, and I can notice that I can write this okay. So if you are not comfortable with how I moved from here to here, you can actually try to expand this, right? So you can, let's do a quick side note here. So if I have dou by dou tau plus dou by dou t, and then I say pull dou v by dou tau right? Remember, this is very reminiscent of your a squared minus b squared being written as a plus b into a minus b, right? But nevertheless, it's good to check if it is true even for derivatives, right? So now I basically have 4 terms coming out of this, right? So I have 2 terms in the first bracket, 2 terms in the second bracket. So now 1 and 3, 1 and 4, 2 and 3, 2 and 4, right? So you will notice that the same cancellation that we see with a squared minus b squared linear algebra that you learnt happens here as well, right? So when 1 and 3 are multiplied, I have dou squared v by dou tau squared. 1 and 4 gives me minus dou squared v by dou tau dou t, and then we have 2 and 3 giving me plus dou squared v by dou t dou tau, and 2 and 4, giving me minus dou squared v by dou t squared. Okay, so we notice that these two cancel off, and what we are left with are only the terms that we originally had in this equation. Okay, so it shows to say that I can have two functions that are two operators operating on the function v, right, giving you 0, right, which means to say that if either operator were to operate with v and give me 0, then the whole thing could be 0, right. So this actually boils down to single derivative conditions on the first derivative. So dou v by dou tau is equal to plus or minus dou v by dou t. Okay, so if I were to set either the second term to 0 or the first term to 0, I'll essentially get 0. Okay, so the wave equation as written on the top essentially boils down to saying that even the first derivative, right, to within a sign has to be the same. So now let's perhaps think for say the two cases, right. So this is now divvying up into two cases. Case 1 where I take the positive sign, dou v by dou tau is plus dou v by dou t, and case 2 where dou v by dou tau is minus of dou v by dou t. Okay, so I have two cases. So I can give you a sample solution, right, which is if I were to take the function v to be t plus tau, okay, just the sum of t and tau, I notice that dou v by dou tau is 1 and dou v by dou t is also 1, right, both of the same signs, and it is equal, right. In fact, if I were to multiply t plus tau with any constant, it will still be true, right. In fact, I can generalize, right, even though I said t plus tau is a solution, we can generalize to say that v can actually be any function of t plus tau. Okay, what I am saying by this condition is t and tau come together always such that I can always find t plus tau in the expression, right. What do I mean by that? Can I give some examples? Of course, right. So I can say one valid function is t plus tau whole squared, right. So this is a quadratic relationship. You will notice that even this satisfies the dou v by dou tau equals dou v by dou t condition, right. Another example, right. So I have exponential e to the power minus of t plus tau the whole square, right. This is a Gaussian function, right. If some of you have heard of this before, even this is a solution, right. So what is this differential equation essentially saying? That you come up with any function, right, where t plus tau always appears as t plus tau, right. So one function that probably will not satisfy this is if I were to say that t e to the minus tau, this will not work, right. So this is a function that does not work. So in the function t and tau should appear as t plus tau, Okay, that is what is the basic requirement. Okay, we can also prove this by simply saying that if I were to say v is some function of t plus tau, then dou v by dou tau is essentially f prime of t plus tau, right, and then dou by dou tau of t plus tau, right. So this is sort of the chain rule. Okay, so you first differentiate the function and then you multiply it with the derivative of the t plus tau itself, right. So that essentially will just be 1, right. So for example, if we took the t plus tau whole squared and I say differentiate it with respect to tau, what will you do? You will kind of say that t plus tau is some variable y, right. So it is of the form y squared. When I differentiate y squared, I get 2y, and then I have to differentiate y itself, right. So I'll have 2y and then dy. So for y it is t plus tau, and then for dy it is essentially the derivative of y with respect to tau, which will just give me 1, right. So that is what I am saying. Similarly, for dv by dt, we essentially have f prime of t plus tau, where now you are differentiating t plus tau with respect to t, which is also 1. Right? So hopefully I have given you a glimpse as to why any generic function, right, as long as t and tau appear as t plus tau in the function, it will satisfy our equation, right. So dou v by dou tau equals dou v by dou t merely requires a function where t and tau come as t plus tau. Okay. So similarly over here I can say that v can be any function g where okay, where t and tau add in opposite signs, right. So v can be any function g, but t and tau have to appear as t minus tau. Okay. So that is what case 2 suggests. So what can we say? Finally, the voltages. So if I were to come with a very generalized solution, right, I can say that v can be some constant times f of t plus tau plus b times g of t minus tau. Okay. So hopefully you take time to perhaps pause at any stage, right. Always you can also rewind and understand what we are trying to do, right. Remember that we are allowing for the transmission line to have voltages and currents that are position dependent, right. This is because we want to say that voltages and currents cannot instantaneously appear at every part of the circuit, right. So when you take a particular transmission line, if it is too long, then I can have different voltages and currents along the length of the transmission line. So we try to come up with a circuit based model which allows for spatial variation in voltage and current, and that led to the telegraph's equations, and these were a pair of equations when reduced to a single partial differential equation looked exactly like the wave equation in mathematics, right. And I am giving you one possible way of thinking of arriving at a solution to the wave equation, right, and which is to say that the voltage which satisfies the wave equation should have a solution of the form that is written in the slide here, which is a times f of t plus tau plus b times g of t minus tau, right? The t and tau have to appear together linearly adding or linearly subtracting, right? So these are the only ways in which I can satisfy the wave equation. So now if I have V, how do I get to I? Is to go back to the telegraph's equations, right? Because the telegraph's equations tell me if I know V, I can get I, right? Or if I know I can get V. Okay, so let's take this telegraph equation, which is dou I by dou x was minus C dou V by dou t. Okay, so remember that dou I by dou x can be converted to dou I by dou tau, right? And I'll essentially get dou tau by dou x, which is square root of LC, right? So remembering the change of variables here, so dou tau by dou x is square root of LC. Okay, and this is equal to minus C times the derivative of V as a function of t, right? So that will give me A times f prime of t plus tau times the derivative of t plus tau with respect to t, which is only 1, plus b times g prime of t minus tau, and the derivative of t minus tau with respect to t is 1. Okay. Now in order to get I simply have to, so I can take the square root of LC to the right hand side, and when I do that I essentially get square root of C by L integral of A times f prime t plus tau plus b times d tau, and I'll have to integrate with respect to tau. So this essentially gives me integral of, actually integral of f prime is f, right? So we just differentiated there, so maybe we can solve the integral directly by saying this is f prime integral of f prime t plus tau d tau is essentially f of t plus tau and here I'll have a minus sign, minus of b g of t minus tau, because there is a minus sign in front of tau, right? So if I were to take g prime t minus tau d tau and integrate it, what would I do? T is a constant when I'm integrating with respect to tau, so I can take t minus tau as a new variable y, right? And you will notice that dy is minus of d tau, right? So you will basically have a minus sign coming from that substitution, and the g prime of y integrate with respect to y gives me g of y, but with a minus sign outside. So of course you will find a constant term which only varies with respect to t, right? But it is easy to show that that goes to 0, right? So I'll take the minus sign that's outside and write I as essentially 1 over square root of L by C times B G of t minus tau minus A of F t plus tau. Okay, so over the last 2 slides, we have essentially solved for B and I, right? So these are closed form solutions to B and I. We are not giving any specific functional forms, right? So F and G can be any function, right? So I gave you some examples in the last slide. It could be the quadratic function, it could be the Gaussian function, it could be something with cosine and sine, right? So we are not actually imposing any form or shape to F or G right now. All we are saying that if there has to be a solution to the wave equation, it will have to have a function f and g where t plus tau and t minus tau come as is, right? So we cannot have any other way in which t and tau combine themselves in the final function for voltage and current, right? Okay, remember that we can always go back to x, right? X is our familiar variable. Tau here is just a stand-in for x, right? So if I were to write the same expressions, a times f of t plus x square root of LC plus b times okay. Similarly, I can write I b times g of t minus x square root LC minus a times f of t plus x square root LC. Okay, so these are our general solutions to voltages and currents that satisfy the telegraph equations.